Course title, General Physics 2. Module 1, Electrostatics, Circuits, Electromagnetism, and Electromechanical Devices. Lecture 1, Introduction to Electrostatics. Welcome to General Physics 2. In this module, we begin with electrostatics, which deals with electric charges at rest. Electrostatics helps explain the behavior of electric charges, electric fields, and electric potentials. Electric charge is a fundamental property of matter. There are two types, positive and negative. Like charges repel, and unlike charges attract. Conductors allow charges to move freely through them, while insulators do not. Metals are good conductors, while materials like rubber and glass are insulators. Lecture 2, Electric Intensity and Coulomb's Law. Electric intensity, also known as electric field strength, is the force experienced per unit charge in an electric field. Mathematically, E equals F/Q, where E is electric field strength, F is force, Q is charge. Now let's consider Coulomb's law. It gives the force between 2 point charges. F equals 1/ for asterisk pi asterisk epsilon asterisk q asterisk q2 / a superscript 2, where F is the force, Q and Q2 are the magnitudes of the charges, R is the distance between the charges, epsilon is the permittivity of free space. This law tells us that the electric force is proportional to the product of the charges and inversely proportional to the square of their separation. Lecture 3, Gauss's law. Gauss's law provides a powerful method for calculating electric fields when dealing with symmetric charge distributions. Gauss's law states, the net electric flux through a closed surface is equal to the enclosed charge divided by the permittivity of free space. Mathematically, phi underscore equals contour integral E the equals Q underscore enclosed / epsilon, where phi underscore is the electric flux, E is the electric field. There is an infinitesimal area element. Q underscore enclosed is the total enclosed charge. This law is particularly useful for spherical, cylindrical, and planar symmetry. Lecture 4, Capacitors and Capacitance. A capacitor is a device that stores electric energy in an electric field. Capacitance, C, is defined as the charge stored per unit potential difference. C equals Q/V. The unit of capacitance is the farad, F. For a parallel plate capacitor, C equals epsilon asterisk A/D, where A is the area of the plates, D is the separation between them. Capacitors are used in timing circuits, filters, and energy storage applications. When multiple capacitors are used, their equivalent capacitance depends on whether they are in series or parallel. Lecture 5, DC current circuits. Direct current, DC, is the unidirectional flow of electric charge. Key components of DC circuits include resistors, which oppose the flow of current, power sources, like batteries, switches and connecting wires. Ohm's law relates current, I, voltage, V, and resistance, R. V equals I asterisk R. Kirchhoff's laws help in analyzing complex circuits. Kirchhoff's current law, KCL, the total current entering a junction equals the total current leaving. Kirchhoff's voltage law, KVL, the sum of the electrical potential differences around a closed loop is 0. Resistors in series, R underscore total equals R plus R2 plus R3 plus. Parallel, 1/R underscore total equals 1/R plus 1/R2 plus 1/R3 plus. Lecture 6, Electrolytic cells. Electrolytic cells use electrical energy to drive non-spontaneous chemical reactions. Key components include anode, where oxidation occurs, cathode, where reduction occurs, electrolyte, ionic substance that conducts electricity. Example, electrolysis of water separates H2 and O2. Electroplating, electrorefining, and battery charging are practical applications of electrolytic cells. The amount of substance deposited or dissolved is governed by Faraday's laws of electrolysis. Lecture 7. Magnetic field of currents. When an electric current flows through a conductor, it produces a magnetic field around it. The direction of this field is given by the right-hand rule. For a long straight conductor, B equals mu asterisk I / 2 asterisk pi asterisk r, where B is the magnetic field, I is the current, r is the radial distance, mu is the permeability of free space. Magnetic fields also exist around loops and solenoids, where they can become strong and uniform. Lecture 8. Electromagnetic induction. Electromagnetic induction refers to the generation of an electromotive force, EMF, across a conductor when it is exposed to a changing magnetic field. This is the principle behind generators, transformers, and inductors. Faraday's law states EMF equals d phi / dt, where phi is the magnetic flux. Lenz's law states that the direction of induced current is such that it opposes the change in magnetic flux. Applications include inductive sensors, electric transformers, wireless charging. Lecture 9. Generators and electric motors. A generator converts mechanical energy into electrical energy by rotating a coil in a magnetic field. There are two types. DC generators produce direct current. AC generators, alternators, produce alternating current. An electric motor performs the reverse action. It converts electrical energy into mechanical energy. Key components of motors include rotor, stator, commutator. In DC motors, motors operate on the principle that a current-carrying conductor in a magnetic field experiences a force F equals I asterisk L times B. This interaction causes rotation and mechanical work. Lecture 10. Conclusion of Module 1. In summary, Module 1 of General Physics 2 has covered the foundational principles of electrostatics, including electric fields and Coulomb's law, Gauss's law for calculating electric fields, capacitors and energy storage, direct current circuits and analysis using Ohm's and Kirchhoff's laws, the function of electrolytic cells in chemical processes, the magnetic effects of electric currents, electromagnetic induction, its laws, and practical uses, the inner workings of generators and electric motors. Each of these topics plays a vital role in understanding electric and magnetic systems, which form the basis of nearly all modern electrical and electronic technology. In Module 2, we will explore AC circuit theory, optical instruments, quantum theory, photoelectric effects, atomic models, wave-particle duality, and semiconductors.